Something is moving through space that should not be moving. It's a black hole, not a small one, not a stellar mass remnant left behind by a dying star. This thing carries the mass of roughly 20 million suns, and it's not sitting at the center of a galaxy where it belongs. It's running. The Hubble Space Telescope caught it, and what it found has forced astronomers to reconsider something they thought they understood, that supermassive black holes stay put. Here's what makes this strange. Black holes at the center of galaxies are gravitational anchors. Everything orbits them. The stars, the gas, the dust, the entire structure of a galaxy organizes itself around one of these objects, sitting more or less still at the middle. That's the model. That's what every observation before this one confirmed. So when a team led by astronomer Peter Van Dokkum at Yale University spotted something racing away from the core of a distant galaxy, they didn't immediately assume it was a black hole on the run. They looked for every other explanation first. There were several, and every single one fell apart. The object they found wasn't a point of light sitting still. It was a streak, a long, thin line of newly forming stars, roughly 200,000 light years from end to end. To put that in perspective, the entire Milky Way galaxy is roughly 100,000 light years across. This streak of star formation was twice that length, drawn across space in a near-perfect line. That shape was the first clue something unusual had happened. Stars don't arrange themselves in lines. They form in clouds and clusters, pulled by gravity into irregular shapes. A line of stars, especially one that long, means something moved through the gas and triggered the formation all at once, like a finger drawn across a dusty surface. Whatever did it was moving fast. Van Dokkum's team calculated the speed at roughly 170 kilometers per second. That's over 600,000 kilometers per hour. For comparison, Earth orbits the Sun at about 107,000 kilometers per hour. The object leaving this trail of newborn stars was moving roughly 6 times faster than that, and it was moving in a straight line directly away from the core of the host galaxy. Now here's the number that was being held back, the one the team sat with for a long time before publishing. The mass. The object at the head of this trail, the thing doing the moving, carried a mass equivalent to roughly 20 million suns packed into a region smaller than our solar system. That is a supermassive black hole by any definition. And it was clearly no longer where it was supposed to be. The question was how. The leading explanation that Van Dokkum and his colleagues settled on involves not one galaxy, but 3, and a sequence of events that unfolded over an enormous stretch of time. It starts with 2 galaxies merging. Galaxy mergers are common on cosmic timescales. When 2 large galaxies collide, their central black holes don't immediately combine. They spiral toward each other slowly, drawn together by gravitational friction, losing energy over millions of years. Eventually, the 2 black holes form a binary pair, orbiting each other at extremely close range. Now, introduce a 3rd galaxy, also carrying its own supermassive black hole at the center. This 3rd galaxy falls into the merger. Suddenly, there are 3 black holes in one chaotic gravitational system. 3-body gravitational systems are notoriously unstable. The physics of what happens next is well understood, but the outcomes are violent and unpredictable. In most scenarios, one of the 3 objects gets ejected. It's a slingshot effect played out at galactic scale. 2 of the black holes exchange energy with the 3rd, and the third gets thrown outward at high velocity. In this case, the team believes the 20 million solar mass black hole was that third object. It got expelled from the core of the merged galaxy system at extraordinary speed, and as it tore outward through the surrounding gas that had been sitting undisturbed in the galactic halo, it compressed that gas as it passed. Compressed gas cools, cooled gas collapses, collapsed gas forms stars. That's the streak. 200,000 light years of newborn stars, each one marking a point in space where the fleeing black hole pushed the gas hard enough to make something new. The trail it left behind is, in a strange sense, a record of its escape. Van Dokkum's team describes the feature as looking like a contrail, the kind left behind by a jet aircraft passing through humid air. The analogy is surprisingly accurate. Just as a jet disturbs the atmosphere and leaves a visible trace, the runaway black hole disturbed the interstellar medium and left a glowing ribbon of star formation in its wake. The Hubble observations were initially made with wide-field imaging. The streak showed up as an unexpected feature during a survey not specifically looking for this kind of object. That matters because it suggests these events might not be as rare as astronomers assumed. If Hubble found one without looking for it, there could be more of them out there, hidden in archival data or waiting in observations not yet fully analyzed. But before anyone accepted the runaway black hole explanation, the competing theories had to be dealt with. The first alternative was that the streak was a jet, a high-energy beam of plasma shot outward from a black hole that was still sitting at the center of the galaxy. Jets from active black holes are real, and they're powerful. They can stretch for enormous distances. But jets don't form stars. They're too hot and too fast to allow gas to cool and collapse. The star formation happening along this streak ruled jets out. The second alternative was a rare kind of dwarf galaxy seen edge-on, a thin, elongated structure that could look like a line of stars if oriented exactly toward the observer. Astronomers checked. The stellar populations along the streak were all young, all recently formed, all pointing in the same direction of creation. A dwarf galaxy would have a mix of stellar ages. This one didn't. That explanation failed. The third alternative was the most mundane, some kind of imaging artifact, a defect in the data. The team checked across multiple observations, multiple instruments, and multiple epochs. The feature held. It was real. After ruling out every other option, the conclusion was forced. A supermassive black hole had been gravitationally expelled from its host system and was now moving through intergalactic space, trailing stars behind it like a comet trails dust. The system containing all of this sits about 7.5 billion light-years away. That's a meaningful number. It means the light Hubble captured left that system when the universe was roughly half its current age. Whatever we're seeing happened long ago, in a younger and more chaotic cosmos where galaxy mergers were far more frequent than they are today. That context matters for the rehook here. The universe we live in now is calmer, but it wasn't always. And the violence that shaped the large-scale structure of everything around us, the threads and voids and galaxy clusters, was largely driven by exactly these kinds of collisions and expulsions. What Hubble caught may be a snapshot of a process that built the cosmos as we know it. Now focus on what the black hole is heading toward, or rather, what it isn't heading toward. The runaway is moving outward, away from its host galaxy. In the opposite direction from the trail of young stars, back toward the galactic core. There's another feature, a bright compact source that appears consistent with an active black hole still sitting at the center of the merged system. That's likely the binary pair that remained after the third was ejected. The geometry holds. The fleeing black hole is not heading toward another galaxy. It's not falling into anything. Based on its current velocity and the mass of its host system, the team assessed whether it has enough speed to escape entirely. The numbers came back close. It's moving near the escape velocity of the system. It may get out. If it does, it becomes what astronomers call a wandering black hole, an object with the mass of 20 million suns drifting through intergalactic space with no galaxy, no stars in orbit, nothing anchoring it. It would be, for all practical purposes, invisible. Black holes don't emit light. Without a surrounding accretion disk of infalling gas, there's nothing to detect. If this one escapes and the gas thins out enough, it simply vanishes from any catalog. That's an unsettling thought. Not because it poses any threat. Intergalactic space is vast, and the odds of this object interacting with anything meaningful are extraordinarily small. It's unsettling because it means there may be objects like this already drifting through the space between galaxies, undetected, uncatalogued, massive beyond comprehension, and essentially dark. The trail won't last. The newborn stars will evolve, disperse, and eventually become indistinguishable from the general stellar background. In a few billion years, the evidence of this expulsion will be gone. What remains will be a supermassive black hole with no address, no context, and no way to trace back where it came from. Hubble caught this during what might be described as the last window of legibility, the brief cosmic moment when the trail is still fresh enough to read. The instrument itself deserves attention here. The Hubble Space Telescope, launched in 1990, it's been operating for over 30 years. The team used its advanced camera for surveys and its Space Telescope imaging spectrograph to characterize the streak. The spectrograph is what confirmed the stellar ages and locked out the alternative explanations. Without spectral data showing that the stars along the streak were uniformly young, newly formed in sequence, the competing theories couldn't have been ruled out so cleanly. The telescope is aging. Hubble has had instrument failures, gyroscope issues, and software problems over the years. Each one prompts concern about how much operational life remains. And yet here it is, more than 3 decades in, catching something no one expected. A black hole in motion, writing its exit across the sky and stars. The James Webb Space Telescope, now operational, can look at this system with infrared instruments that penetrate dust in ways Hubble can't. Follow-up observations are expected. The goal would be to better characterize the mass of the runaway, track the velocity with more precision, and search the surrounding region for additional evidence of the three-body interaction that started all of this. But the discovery itself belongs to Hubble. And it belongs to the moment someone was looking at data from a survey aimed at something else entirely and noticed a line that shouldn't be there. Science works that way more often than textbooks suggest. The most important finds don't always come from targeted searches. Sometimes they come from a scientist looking at an image and thinking, "That's wrong. That doesn't belong." What is that? Van Dockum has described his initial reaction to the streak in almost exactly those terms. He saw the feature in the data, assumed it was an artifact, and started trying to explain it away. The explanations didn't hold. The feature stayed. And eventually the team had to accept what the data was telling them. A black hole 20 million times the mass of the Sun had been thrown out of its galaxy and was crossing space at 600,000 kilometers per hour, and Hubble had photographed the trail it left behind. There are estimated to be hundreds of billions of galaxies in the observable universe. Most large galaxies have a supermassive black hole at their center. Galaxy mergers have been happening throughout cosmic history. The three-body ejection mechanism is not exotic. It's a predictable outcome of gravitational dynamics when three massive objects interact at close range. The uncomfortable implication is that this probably isn't rare. It might not even be unusual. What's rare is catching it, finding the system at the right moment, with the right instrument, in the right configuration for the evidence to still be readable. Which raises a question the team has been sitting with. How many wandering black holes are already out there? There's no clean answer. Estimates vary depending on assumptions about merger rates, ejection probabilities, and how often three-body interactions actually produce an expulsion rather than a coalescence. But even conservative models suggest the number could be large. Some researchers have proposed that our own Milky Way galaxy may harbor wandering black holes, objects ejected from earlier mergers in the galaxy's history that now drift through the outer halo, dark and silent. We can't see them directly. We might detect them through their gravitational effects on stars that pass too close. But the searches are difficult, and results so far have been inconclusive. The runaway that Hubble caught is, in a sense, the clearest example we've ever had that this process is real and has happened at least once in a confirmed, documented way. That changes the theoretical landscape. It moves the three-body ejection scenario from plausible mechanism to observed phenomenon. And that changes what astronomers have to account for when they build models of how galaxies evolve, how black holes grow, and what happens to the enormous amounts of mass that don't end up in the final merged object after a galactic collision. The streak itself, those 200,000 light-years of young stars, is, depending on how you look at it, either a scar or a monument. A scar left by something tearing through space at extraordinary velocity. Or a monument to a chain of events that began billions of years ago when three galaxies, each carrying its own enormous gravitational anchor, fell into each other and couldn't hold all three. One of them had to go. It went at 600,000 kilometers per hour, pushing gas into stars as it left, drawing a line across space that lasted just long enough for a 30-year-old telescope in low Earth orbit to catch it before the evidence dissolved back into the background. The host galaxy is still there, 7.5 billion light-years away, now carrying what's likely a tighter binary pair at its core. Two remaining black holes still spiraling toward each other, still losing energy, still heading toward an eventual merger of their own. That merger, when it happens, will release gravitational waves powerful enough to be detectable across enormous distances. But by the time that happens, the runaway will be long gone, moving through the dark between galaxies, invisible and enormous, with nothing ahead of it and a fading trail of stars marking where it came from. The universe has a way of leaving evidence. It rarely leaves it for long. This time, we were looking at the right moment. Thanks for watching, and I'll see you in the next one.